I can see your hand there. It's recorded.
Okay. Can you see, stay up there for a second. Can you see this? How much of this can you see? Can you see this part?
I can see, not
Here?
your thumb.
Here?
Yeah, I can see that.
Okay, good. All right. Okay, so scientific notation. All right. Yeah. Yeah, I'm going to edit that out. Okay, so scientific notation. First off, let me explain why we talked about scientific notation. So think about this, right? We started out counting like this. We started out with, let me make marks, and look, that's 6 right there. You know, and that was a basic system for counting. And this is good for numbers up to 10 or 20 or 30, but then it starts to get irritating, right? Because you're making a lot of marks, and if you got 20 hash marks, it's hard to count. So then they advanced to something better. They came up with 1, 2, 3, 4, 5. And now you can count by 5, 10, 15, 20, and so on. That was an okay number system, right? But then when you get to numbers like 150, it starts to become cumbersome. So then what was next after that? Roman numerals, right? These things, you know, that's number 15. That's not right. That's number 15 in Roman numerals and so on. And this was a pretty good system. But if you wanted to write really big numbers like 152,871, that would start to be difficult. So then we came out with our modern numbering system, 1, 2, 3, 4, and so on. And this is what we use most of the time because we don't usually deal with numbers that are too big for this. This is good for most of what you see every day. But eventually you do get the numbers that are really big, and it becomes cumbersome to have to write them in everyday numbers. Let me give you an example. Avogadro's number, which is the number of atoms or molecules in 1 mole of something, is this number here. That should be a 2. So you think about it, if you had to use this number to do like calculations or add or subtract, and you had to write it several times on a piece of paper, this would become a really big waste of time. Right? You would want a way to write this smaller. So that's why we came up with scientific notation. For numbers that have more than 15 digits over a trillion or a quintillion or whatever. So then we use 6.022 times 10 to the 23. And this is a little bit easier to deal with than all that. So that's why this exists. Now the rules are pretty simple. There's really only one rule. Always, 1L, always put the decimal to the right of the first non-zero. You can see like I did here. After the 6, you get a decimal. All right. So let's deal with some scientific notation. Let's see how to write numbers. So let's start with something like 100. So how would I write this in scientific notation? Yeah, exactly, 10 to the second power. I could write 1 times 10 to the second power if I wanted to, but it's kind of silly for that. And what about this number? 10 to the third power. Now if I had something that wasn't just a 1 with zeros after it, let's suppose I had 2,000, what would this be? 2 times 10 to the third. 10 to the third is 1,000, so 2 times 1,000 is 2,000. If I had 2 million, what would I write? 10 to the sixth. All I'm doing is counting back from the end, 1, 2, 3, 4, 5, 6, until I get the decimal before the in front of the to the right of the first non-zero number. So 2 times 10 to the sixth power. Okay, you get 6 times, it's 10 to the 6th. All right, so that's easy enough. Now, if I have, let's say, let's do this. 2, 4, 0, 0, 0. Okay, how am I going to do that? Okay, so I could write 24 times 10 to the third. And understand that this is equal to the answer, right? I could also write 240 times 10 to the second. I could write 200, or I could write 24 times, I just did that. I could write 2,400 times 10 to the first. Right? There's a lot of different options, and all of these equal 24,000. But for consistency, we go back to this rule, which is that we're going to put the decimal in front of the first non-zero number, to the right. So it's going to be 2.4 times 10 to the fourth.
Oh, you just moved it.
Yeah. So I moved it 4 times to get it to where the decimal's to the right of the 2. So always have only one non-zero number to the left of the 2. So like a number that has, yeah, you get the idea.
Wait, so whatever the number, number is, and you put that in time, the decimal place?
Yep. Let's do another one. Let's do 20,400. What am I going to put here?
2.04.
Exactly. I'm going to go 1, 2, 3, 4. So it's going to be 10 to the fourth, and it's going to be 2.04 times 10 to the fourth.
You don't just put the zeros at the left?
No, because those zeros don't add any value. 2.04 and 2.0400 are the same number.
No, I meant for the power of 10 to the second. Like
No.
I was the one that actually put on it.
Because I had to move this to here so that there's only one non-zero number to the left of the decimal. All right. Now, what if I had something like this? 230.38. Let's do this one. How many times am I going to move the decimal here? Twice. Because again, I want the decimal to the right of the first non-zero. So 1, 2. So it's going to be 10 to the power of 2. Now I got to write all these numbers here because they're non-zeros, right? So I got to put 2.3038. All that has to go in there times 10 to the 2. All right. That's enough of that. I think you get the point. Questions? All right, let's do this. 100 is 10 to the power of 2, right? What's 10?
Oh,
1 to the power.
Yeah, 10 to the power of 10, right? 10 to the power of 1.
yeah.
Okay, so what is the number 1?
1 to the power.
Yes, but that's not what I want. 10 to the power of what? It's got to be 0. Every time we divide this by 10, this number goes down by 1. So 1 is 10 to the power of 0. In fact, any number to the power of 0 is going to equal 1. What if I divide this by 10? I get 0.1. What's that got to be? Negative 1. 10 to the minus 1. And which, by the way, is the same as 1 over 10, right? You can write it either way. It doesn't matter. What if I divide this number by 10? I go 0.01. What's that going to be? 10 to the minus 2. And we also know that this number is the same as 1 over 10 squared, right? And 10 to the minus 3, in fact, is 1 over 10 to the 3, right? And 10 to the minus 4 is 1 over 10 to the 4th. So anytime you have a negative, you can just throw it on the bottom and make it positive. It's the same thing. Negative just means you're dividing by 10 to the power of whatever that thing is. Questions? All right, last thing, we're going to move on to adding and subtracting. Addition. Plus subtraction. If you guys catch me going too fast, let me know. Slow down. All right, so addition. Let's start off with something small. Let's do 5 times 10 to the power of 3 plus 3 times 10 to the power of 3.
You not do it.
Which thing?
Maybe the time.
The x's?
Yeah.
Well, we use x's in scientific notation. No, what do you want, dots?
Yeah, that's what I do.
All right, you do dots.
Alright.
Okay, so what's the answer? Is that right? Yeah?
No.
No? What do you think? What do you think it is?
I didn't put that one back. Yeah, I'm going to make it 10 to the 6.
You say 8 times 10 to the 6th? Is that right? I use that 10 of the voice. You just keep saying no, right? Okay.
No, I think the first one.
I mean, first one? Let's find out. What is this number? The real numbers.
500.
5,000. 3 zeros. 5,000. What's this number? 3,000. We had 5,000 plus 3,000. What do we get? What's this one? Then the third. So anytime you're going to add two numbers that are in the thousands, you expect your answer should come out in the thousands, right? Shouldn't come out in the millions. So if we had the same exponent, all we have to do is add the two coefficients together, and then the exponent stays the same. Now, you won't always be able to do this, so you got to remember the rules, right? It's easy to do for 10 to the third, but if I gave you a problem like this, let's say 7, yeah, we'll do 7. 7 times 10 to the 45 plus 2 times 10 to the 45. You know, this one you can't write it out. You can't say, let me write 45 zeros and figure out what the answer is going to be. So you got to know the rule. What's the answer going to be here? 9 times 10 to the 45. So you always make sure keep the exponents same. Questions?
Now, what if the 2 was a 3? Then it would be to 46?
Yeah, exactly. Because then you would have 10 times 10 to the 45, which you would just make 1 times 10 to the 46 to put it in proper scientific notation. All right, now let's do something where they have different exponents and see how we do with that. So let's say we have 6 times 10 to the power of 4 plus 2 times 10 to the power of 3. All right, what do you think the answer is going to be?
I don't know.
What is it, 16?
Is it looking for the 7?
That's what you said?
No, I don't know.
Anybody else? What do you think?
8x.
Other than
Or, I mean, 8 times.
So you both agree on this?
Wait, but mine was on the first 58.
Which one? Okay. Anybody else? All right. So let's take a look again at the real numbers and see what we get. What is this number?
60,000.
60,000, right?
It's 2,000.
2,000.
Which is 62,000.
This guy was close.
6.2 times 10 to the third.
What is 62,000? 1, 2, 3, 4. Should be 6.2 times 10 to the 4.
How did you get that?
Did he get it?
That's what I
He's
got.
smart.
Well, you already explained it.
I will.
So do you?
I'm going to show you the process. Hang on. I gave you the answer. Now let me show you how you get the
The
answer.
higher one?
It's going to be the higher one, but let me explain it first.
Oh, don't even say anything, guys.
So we got 6 times 10 to the 4, same problem, plus 2 times 10 to the 3. So what you do is, we have different exponents, we have to take the smaller one, whichever one's smaller exponent, and we got to make this bigger. We got to make this the same as the other one. Now, I can't change the value of this number. This still has to be 2,000, but I have to rewrite 2,000 in a way that it's times 10 to the 4th. So, times 10 to the 4. What number do I have to multiply by 10 to the 4 to make it 2,000? Well, if I make this 1 bigger, I got to make this smaller, right? I got to make this 0.2. So, if I make the exponent 1 bigger, I got to make this number 10 times smaller. Well, 10 to the 4th is 10 times bigger. This has to get 10 times smaller. So let's move the decimal over. All right. If you plug it in your calculator, this number is still 2,000. It's still the same number. I didn't change the value. I just changed this, so I moved the decimal over. And then, of course, it's easy. 6 plus 0.2 is just 6.2 times 10. Questions? How many people are getting this so far? How many people that just got lost? Couple? All right. Let's do another one like this. Let's do 7 times 10 to the 11 plus 4 times 10 to the 10. Okay? So we look at these two things. This is the smaller exponent, this is the bigger exponent. So I gotta make the smaller one be the same as the bigger one. So I have to take this 10 to the 10 and make it 10 to the 11. I hope you understand 10 to the 11 is 10 times bigger than 10 to the 10, because this number went up by 1. So now I gotta divide this by 10. I gotta make it 0.4. This one stays the same.
7.4 times 10 to the 11, right?
7.4 times 10 to the 11.
I got it.
Good? All right. I got one more example to do and then we're finished. What if they are two numbers apart? So let's do 8 times 10 to the 5 plus, let's say, 5 times 10 to the 3rd. Okay?
0.05
Yeah.
times 10 to the 5th.
Yeah, that's what it's going to be.
Wait, what?
Oh, wait, don't listen.
No.
Okay, so this is a bit too smaller than this. What's wrong? What don't you get?
Let me see everything.
I'm gonna do the problem first before I give you the answer. All right, look. I need to make this 10 to the 5th, right? I need to make this the same as this one. They both gotta have 10 to the 5, right? So to make this 10 to the 5th, this number's going up by 2, right? I move the decimal twice. 1, 2. 0.05.
I just said that. Times 10 to the 5th.
0.05 times 10 to the 5th. So all I did was, since this went up by 2, I had to move the decimal over twice. Yep,
Oh, because the other one's only went up by 1.
exactly.
Oh, that's why it's different.
Hold on, let me write that.
Yeah, I'm about to mark down all this work. Hold on, this is
It's easier too to write it out like that.
So you just now started thinking this?
Oh, no, I did, but I just wasn't doing the work.
Okay. Yeah, like I was just doing that for no reason. I'm not going to write that down. All right, so 8 plus 0.05. You should get 8.05 times 10 to the 5. All right, I'm listening to questions.
I have a question.
Yeah.
What are you doing with that 10 with the 5 right next to the 8?
Here.
No, at the bottom.
Here?
On the bottom.
This one?
Yeah.
I just rewrote it.
Why did you have to do that?
Well, this number here, right? I wrote that number like this. These are the same number. They're both 5,000. I just rewrote it differently so it has 10 to the 5 in it. And then I still got to add it to this afterwards. I still got to add it to this afterwards. So I just rewrote this down here just to make it neat. That's all. What else?
Can we do another one?
All right, we can do another one.
Make it like 8.
Let's
This is
do.
still addition and subtraction?
Yeah.
Make it like 8 apart.
What's subtraction? I don't see no.
Well, okay. So this is still addition.
Yo, you're so childish.
The rules for subtraction are exactly the same. You make them the same and then you subtract. Since subtraction and addition are basically the same thing, I'm only going to do problems with addition. If you want, I can do one with subtraction.
No.
Okay, so let's just do one more with addition. Let's do 3 times 10 to the 7 plus 9 times 10 to the 9.
Oh, wait, so what this, we gotta move it, so that's a 3, right?
Yeah, so which one's smaller first off?
The 10
The
to
3.
7.
All right, this one here, right? So that's the one we got to change. So we got to make this 10 to the 9.
Alright, so would it be 3.09 times 10 to the 7?
Hang on, slow down. Write out your work. I'm making this a 9. So I got to move the decimal 2 times here. 0.03. And now we add them together. 9 we get 9.03.
10 to 9. Got this.
Whichever one is small, has a smaller exponent, that's the one that you're changing.
I got this.
Alright, let me pass this out.
No.
I'll do a vote for that.
Don't worry, this is it'll be okay. There's two separate worksheets that each like one page. I made them separate in case I taught these as separate lessons. Yeah. Today is
Oh,
lab
yeah,
day.
yeah. Are we working on it, or like when this bell rings, is it gonna be this homework?
Yeah, but I mean, if you, I'll give you a couple extra minutes after the bell rings for people to count this. No problem.
Yeah, I'm gonna do one. I'm sorry.
Bobby, do me a favor. Turn the camera off.